Hi everyone, my name is Fat. Today I will present our work, EmbryosFormer, Deformable Transformer and Collaborative Encoding-Decoding for Embryo Stage Development Classification. First I will introduce the problem settings. During the IVF procedure, a patient is stimulated to produce multiple fertilized embryos. The embryo viability is assessed based on their transition phase between stages of development, which takes several days to finish. Thus, a technique with microscopic camera captures embryo images at discrete time and create time-lapse videos that summarizes the whole development process. And clinicians have to watch these videos frame by frame and choose the best embryo with the highest probability of pregnancy. This manual job is at high risk of misclassification. In this work, we develop an efficient method for this task, given the time-lapse video as input. And we need to output the stage prediction at each time with the constraint that the embryo development process is monotonic increasing. Recent methods process a window of frames at a time, in which frame-level features are obtained by 2D CNNs followed by recurrent network to extract temporal information. However, the window length is fixed while the embryo stage times vary. This approach could lack the global context of each development stage. Moreover, a well-learning feature of the embryo stage also benefits several downstream tasks, such as stage quality prediction besides stage classification. And processing the entire video at a time is an efficient way to embed the monotonic constraint. As the embryos develop from stage to stage, we can set that each embryo stage is technically a segment of consecutive frames. And with the constraint that these segments dominate the entire sequence length and they cannot be overlapped with each other. Solving the problem this way, we propose an encoder-decoder architecture. Specifically, the embryo image-based features are first extracted with a pre-trained CNN to obtain sequence features and go through the deformable transformer encoder to obtain embryo embeddings. At the decoding branch, we initialize the number of queries equal to the number of stages that are needed to classify. These queries are then performed cross-attention with encoded features and self-attention to obtain the final embeddings for all stages. Linear projection heads are added on top of both branches to predict image-wise classification and stage-level segmentation of stage width and center position. We make use of the stage global context from decoder to align the coarse image-wise predictions in encoder to an appropriate segment in the collaboration head. The final frame-wise classifications are formulated as a multiplication of two components, position weight and attention weight. Position weight is based on the frame orders and its related distance to each predicted stage segment position. The more a frame is far from the stage area, the lower probability that this frame belongs to that stage. Here T is a temperature constant. Attention weight is obtained by the cross-attention of the embryo's embeddings to the query embeddings. In this work, we also propose a real-world human embryos dataset that is well pre-processed and annotated by 3 clinicians. With the raw captured time-lapse videos, we detect and crop the embryo area and remove those that are too misaligned and missing a lot of the embryo's morphology. The dataset consists of 440 time-lapse videos around 150,000 images and is collected from 112 patients. We conduct extensive experiments with recent methods on the 2 datasets to measure the performance of our proposed network. It can be observed that the performance of EmbryosFormer stands out against the others by a large margin on both datasets. Finally, we conduct ablation experiments on the 3 proposed heads and benchmark the efficiency of EmbryosFormer with the recent methods. Each module plays an important role in the whole network. While classification head produces precise frame-wise predictions, segmentation head embeds the monotonic constraint in its segmentation output. Collaboration head combines them to improve the per-frame predictions and achieve the highest result. And our method is also efficient at inference time. Thank you.